Yes, hello friends. It's good to be back with you. It's been quite some time without us doing a video, and I thought today I should do a video, and I want to speak of some basics, And today I'm going to focus on RC columns, just basics, zero mathematics in RC column design. Just to get into it, let me want to focus on RC column design. Well, so the code of reference we're going to use for the purpose of this video is BS 8110, and somebody could be asking what exactly is a column. That is the first place, right? What exactly is a column? Somebody could be asking this. Well, a column is a member which is responsible of transferring loads from the beams down to the foundations, so that if you have a structure, let's take for example, you have a building. This is your floor level. Pardon my sketches. So this is your floor level, and this is a slab. This is a slab is transferring these loads to these beams. The beams transfer those loads to these columns over here. So columns are these vertical members which transfer loads from beams to the foundations. These vertical members here. So if you look at BS 5950, that is for steel. If you look at BS 5950, it defines columns as members which carry both axial stresses and also the bending stresses, so that if you have a column, then this column is subjected to axial stresses, that is axial forces, and it is also subjected to the bending stresses, and it defines a strut as a member which is only subjected to axial stresses, that is for steel design. For this case, we just want to focus on concrete design, and so we're just going to handle our column as a member which transfers both the axial and also the bending stresses. Well, so what exactly should you consider, before you even start designing your columns? What should you consider, well, for me, what I would consider in the first place when I wanted to design my column is whether my column is slender, is a short column or a slender column, a short or slender column. What does these things really mean? A short or a slender column. Well, there are definitions from the codes which we have to follow. BS 8110 defines a short column as one where the effective length, we call it length effective, a subscript A, the effective length divided by the dimension of the column in the direction of bending. So if we have well, I think let me do a sketch for that to enhance a bit of understanding, is when we come to this definition. Well, if you have a member, say you have let me do a cross section. You have a 200 by 400 column. This 400, then you also have a 200. This 200, this 400. Well, if this column is bending in this direction, if this column is bending in this direction, you know, then the depth which is responsible for bending is our 400 here. That is very important, you know, because I think it is something which people do miss. If it is bending in this direction, the depth which is responsible for that bending, to take care of that bending, is the 400, right? But if it is bending in this direction, then the depth which is responsible for that bending is 200, right? Is 200. Yes. So what happens if you want to know whether your column is short or slender? Then if you take the effective length of your column, then you divide that effective length by the depth of the column responsible for bending, then you will know whether your column is slender or a short column. So for example, in this case, let's say we have a column which is maybe 3 meters in height, a 3-meter column. You know, you have a column which is 3 meters, and you want to know whether this column is short or slender. You know, what do? Number one thing is you have to find the effective length of this column. You know, effective length. What is effective length? Well, we have something called the clear height of a column and the effective height of a column. So if this is a column and this is our upper floor, this is our lower floor, right? Then the clear height between supports, this one here is called the clear height. You know, clear height. That is clear height. Clear height is defined as the L naught. You know, L and subscript 0. That is the clear height. What of effective height? You know, effective height is just this clear height. You know, you multiply by the effective length factors. You know, so what are these factors? So effective length is simply, you know, you take effective length factors called beta for this case, the chords and beta, then you multiply that by the clear heights. You know, how do we get these? Then the next thing is, how do we get this beta here? How do we get this beta here? Well, beta is tabulated in the code, and it depends on the type of restraints we have at the ends. You know, you might have a column which is fixed at the bottom, but then it is a cantilever at the top. That means it is free. It is free to rotate here. It is free to move. You know, so depending on the type of restraint you have on the top, you can get your values for beta. And this also depends whether it is a braced structure or an unbraced structure, because if it is braced, then the value of beta changes, is different. You know, if it is unbraced, the value for beta also changes, right? Yeah, so you have to know. Most of the time our structures are usually really unbraced, because most of these structures doesn't have a shear wall, and therefore they're not braced. They're sway frames. You know, so you have to really know and pick the right value for beta. You know, so let me just speak a little bit about this beta. I think it is very important. So let me just talk a bit about it. You can do a new slide for that. Well, if you have a column, you have a column here. That is a beam. This is also a beam, right? You want to get the value for beta for this column. You know, so if this column, say is a 400 by 200 column, then our beam here is a 450 by 200 column. That means our beam here is deeper than this our column in other directions, right? So if the direction of bending in this case is this direction, that means our depth in bending is this 200, right? And the depth of the beam which is restraining this column is more than the depth of the column which is responsible in bending. Therefore, we classify this our member, we classify this end as fully restrained. This end is fully restrained because the beam which is restraining this column is deeper than the depth of the column itself, right? If the same is true for the bottom case, then we also classify this one as fully restrained. Otherwise, it could be partially restrained. Partially restrained is when, let's say we have a column which is let's say this column is bending in this direction. That means the depth responsible for bending is 400, and let's say we have a beam of 200 by 300, right? So what will happen is that the depth of the beam which is restraining our column is less than the depth of the column which is responsible for bending, right? So this our member will be partially restrained. That member is partially restrained, you know. This member is partially restrained. So depending on the end condition here, you can get the values for beta, and depending whether the structure is braced or unbraced, you can get the value for beta, you know, in the code books. You know, from that you can go ahead and find your values for effective lengths. As I said in the previous slide, is that our effective length is equals to that value for beta, which depends on the end condition. You multiply by the clear height of the column, right? So if this value, well, after getting this, we can now find the slenderness ratio. There's something called the slenderness ratio. How do you find the slenderness ratio? You know, the aim is to know whether our column is slender or short column, right? We want to know whether the column is slender or a short column. So the next thing after finding the effective length, let us say the effective length for a column is 3 meters. 3 meters, right? So we need to find what is called the slenderness ratio. Slenderness ratio is denoted by the letter lambda, you know. So slenderness ratio is just the code describes slenderness ratio as the effective length of that member, you know, effective length you divide by the depth responsible for bending, you know. So if this member is bending in this direction, you know, so let me just draw a column in 3D. A column in 3D. So if this column is bending in this direction, then the depth which is responsible for bending is this depth here. That is the depth responsible to take care of bending. But if it is bending in this direction, this large depth is responsible for bending. That is simply what I mean, right? That is simply what I mean. So in this case, if it is bending in this direction, then the smaller dimension is responsible for that, you know. So you take the effective length, which is LE, we divide that by our dimension there, which is responsible for bending. So in this case, if our effective length is 3 meters, okay, let me call this dimension D. If our effective length is 3 meters, 3 meters, that is 3000 millimeters. you divide that by the dimension responsible for bending. In this case, the dimension which is responsible for bending is this 200 right here. So if you divide this by 200, what do you find? This one will give you roughly, 15. And the BS code has a threshold where you can classify a column as slender or short column. So for breast structure, a column is called short. If the effective length divided by the dimension responsible for bending, is less than or equals to 15. Is less than or equals to 15. So if it is greater than 15, then this column, that is for breast, if it is greater than 15, then this column is called a slender column. Then for unbraced, okay, this one is equals to, less than or equals to 15. We call that a short column. If it is greater than 15, we call that slender column. Slender column. If it is greater than 15. If our slenderness ratio, which is defined here, is greater than 15, we call that a slender column. What about for unbraced structures? We have also unbraced structures. In most of our structures, we don't have bracings. We don't even have shear walls. So they're usually unbraced. So if it is for unbraced, the value for lambda here, should be less than or equals to 10. Less than or equals to 10 for it to be called a short column. Otherwise, if it is greater than that, if it is greater than 10, then that is a slender column, right? But what is the importance of finding all this? What is the importance of doing all these checks to see whether it is slender or it is a short column? Or, well, very important. That is very important. That is very important. Let me just tell you why you need to do that. Let me just tell you why you need to do that. So what is the importance of knowing whether it is slender or it is a short column? Well, a slender column is a column which will fail by buckling. Does that mean if you apply a load, if you have a column and you apply an axial load, this column will fail by buckling. That is what we call a slender column. It will fail by buckling. What that means is this column, the material will not yield. It will fail by buckling before it reaches the yield strength, which is very catastrophic. So we really need to know whether our column is going to fail by buckling, so that we design for that. Otherwise, this column, if it is a short column, then it will just fail by crashing. So we just need to design for that. We don't need to bother so much with the buckling thing. It will just fail by crashing, maybe at the midpoint, just crashes. So how do we take care of this buckling? in our design. What happens is that if we realize that it is a slender column, then what we do is that we design for additional moments, which is caused by that deflection. So there is this deflection here, delta. This one will cause additional moment, in this column. So notice that if this column deflects to this point, different color will be good for that. If this column deflects from this point, from this point to this point, that means we now have an axial load here which is acting at a distance delta. So if you take that axial load, take the axial load P, you multiply that by delta, you get additional moment, right? This is simply it. That is simply the idea. You want to get this deflection here, multiply that by this load here, and you will know the additional moment which is in this column. So if we know the additional moment here, we can design it for that extra moment so that it will not fail by buckling. So that is really it. That is really the concept of columns, RC columns. Just to summarize, you need to know whether your column is short or slender. For you to know whether it is short or slender, what you do is, first of all, you need to know the clear height. Clear height is the clear distance between the end restraints, between beams or between columns, restraining that member. After knowing the clear height, you have to know the effective height. How do we get the effective height? Effective height is equals to the clear height times beta, where beta is the effective height factors. This is given in the code books, depends with the code you're referring to, and this beta also depends whether the column is in a braced system where all the lateral loads is taken care of by the lateral load resisting systems. Otherwise, you should design for unbraced systems. Well, from that you can get your slenderness ratio and check it with the slenderness limits given in the codes to know whether it is slender or not slender. If you prove that it is a slender column, then you have to design for additional moments. So apart from the original moments which are acting in this column due to the gravity loads, or due to the wind loads, you have to design for additional moments which is caused by the deflection, due to buckling. So that is it. If you really like this, you kindly subscribe to the channel so that you will get such videos. Make sure you share this also with your friends so that they can really learn. They can also learn because we really want to share knowledge. A society is so good when everyone knows what they are doing. That is the society we want to build. Well, you can also leave me a comment in the comment sections so that I will always pass through there and see. If you have any doubts in this, please also put in the comment section. I will love to interact with that and also share with you knowledge. Thank you so much for being patient and watching this. We will meet again in the next video. Stay safe. Thank you.